Okay, so let's recall what we want to implement. We want to have a batch parallel priority queue with a data parallel insert operation that inserts a constant number of elements per processor, and delete min star operation that deletes the p globally smallest elements and assigns one of them to each processor. Inspired by the Karp-Zhang algorithm, what we want to do is we want to keep one local cube for each processor, and the idea is to insert elements into random queues. So we send them to a random processor and there it's inserted. And the idea behind this is that then every processor has a representative view on what are small and large elements. It's not a precise thing, but the idea is to use a global collective operation to make this precise. Okay. Yes, that's what we have extracted here from this branch and bound approach. And let us summarize a few things we get by the random placement of the data. So several things hold with high probability. In this case, high probability means probability at least 1 minus p to the minus c for constant c that we are free to choose. It will often be something like 2 or 3 or 4 or so. So we have kind of a balls and bins situation in several respects here. So if we are allocating order p balls into p bins, then it is known from stochastic research, and we can actually show that using Chernoff bounds, that no local queue will receive more than order log p divided by log p elements. Also, if you look for the p globally best elements, it suffices to look among the order log p smallest elements in the local queues. And we have some load balance with respect to the number of elements n, namely each queue will contain order n over p plus log p elements. So all of these things can be shown using Chernoff bounds, but I'm not going into that. So, and I will present the implementation of 2 steps. One, a relatively simple one that's slightly suboptimal, and then I will refine that further. So insertion is relatively easy. In particular, the communication cost can be bounded by this number T collective, which in particular includes sending a constant number of constant size messages to random processors. So, and from the page before, we know that no processor will receive more than order log p over log p elements, and the local queue will contain about n over p elements. So the cost for local insertion, assuming a priority queue with local insertion cost, would be this log p over log p log n over p. So roughly speaking, it's log squared something, which is a bit more than we would like, but maybe in practice it would be actually dominated by this communication overhead, which is logarithmic but with much larger constants. Maybe that's also a nice opportunity to look at advanced data structures, right? So there are priority queues that support much faster insertion, and then we would basically get rid of this log n over p term. But we have to be a little bit careful, because some of these advanced priority queues are efficient only in an amortized sense, and that's dangerous in a parallel setting, because we have a global synchronization here. It suffices if one of the processors is slow, so that all other processors have to wait. So in general, be careful with amortized efficiency because that might slow down parallel algorithms that do too much synchronization. We will actually later use amortization, but then make sure that the processors also synchronize with respect to when they do something expensive. Okay, so of course the delete min operation is a more complicated thing, but our observation about the random distribution gives us one key observation. It suffices to look at the top log p elements in each local queue, right? So we just put them into a temporary data structure Q0. So this is a single programming multiple data pseudocode. Each processor gets its local priority queue Q1, and we know the number of processors. Now we run another basic toolbox operation. Now we need a parallel algorithm for selecting the p globally smallest elements from the union of all the Q0s. And I will explain how that works later. So what this means is we have each processor has some fragment of this global set M in its local memory. And we have seen in the example that maybe some processors have several of the elements, some have none, right? So we need an additional step of assigning these elements to the processors. We do that by giving them numbers between 1 and p, and that can be done using a prefix sum. Then there's also a checker. I mean, this is a randomized algorithm, but we want that this delete min star operation has a deterministic semantics, namely that it really returns the p globally best elements. And of course, it might be that very rarely we didn't get all the p globally smallest element because one local queue contains more than this order log p of them. But we can check that efficiently by computing on the one hand a maximum reduction over the elements in M, and on the other hand a minimum reduction over the smallest elements of each local queue. So that's basically two reductions that we can do in a single step with a vector length of 2. And if the maximum element returned here is larger than the minimum element that we ignored, then we need to do some special case treatment. But we can make that probability polynomially small, and then we can afford expensive things to repair it. Actually, if you would be very efficiency eager to have this very efficient, we might even allow that this occasionally fails, and we can then actually do that relatively efficiently by just fetching more local elements occasionally. So actually the overhead would not be super big. Okay, and then this was in this current implementation only a temporary data structure, so we now empty it back into the other queue, which is local. So let's analyze this algorithm. Removing locally is order log p delete min operations in, say, a binary heap of size n over p. So it's log p log n over p. We will see later that the selection operation can actually be done in time order t collective with high probability. As I said, enumerating the elements is basically a prefix sum, and delivering it can also be done in time order t collective. So what we have here is somehow the reverse of what happens at the insertion. In insertion, we had elements that were reasonably uniformly distributed over the processors, and they were sent to random destinations. Here we have something like random sources of the data, which is sent in a perfectly balanced way with respect to the destinations, but the cost of that is basically the same. The verification is time order T collective for checking, and for repairing we have something that is certainly possible in time polynomial in P, but the probability for this is polynomially small. We can make this polynomial have a larger degree than that polynomial. And then overall that's just a lower order term. Yes? And then the local insertion of the data back is, so inserting this is no more expensive than the removal cost we had before. So this is not quite satisfactory, because both for insert and delete min star, we have this two logarithmic factors that are multiplied. The communication is already fine, it's all order T collective, but we are doing somehow too much local work. And I now want to present a refined implementation that avoids this overhead. And the idea is very simple. We avoid this ping pong of order log n smallest elements that are removed and then reinserted in the queue all the time. So the idea is to split this queue such permanently into Q0 and Q1, maintaining the invariant that the size of Q0 is always order log P. And then basically the basic scheme remains the same, except that the local queues are now split into a large part and to a small part of the locally. Well, we will see they will not always be the smallest elements here, but they will at least contain them. That's the invariant we maintain. Okay, now how does that affect the operations? For insertion, sending the data is the same as before. The local insertions will simply merge the received elements and the new elements. So the idea here is that Q0 is actually maintained as a sorted sequence. And maybe for the flipped classroom, you can think how exactly we get at an overall cost of order log P here. Because the maximum number of received elements was this complicated log P over log P, right? Of course, if that's all, then Q0 will grow and grow and grow, right? So we have to maintain the invariant that the overall size is at most order log P. And what we are doing is that we are emptying Q0 every log P iterations. So then we have a Q of size order log P, insertion time of order log n over P. So, and then in an amortized sense, this cost is amortized over log P iterations, so the overall cost is only order log n over P. It may sound like I have cheated here a little bit, because the worst case number of elements received is order log P over log P. The number of iterations I do this is log P, so it sounds like the worst case could be log square P over log P elements in Q0. But that's actually not the case, because once again, using Chernoff bounds, we can see that the overall number of elements received over log P iterations with high probability will be the expected number of elements received, namely that's order log p. Basically what happens here, yes, some processors will receive log p over log p elements, but it will always be different processors. It's very unlikely that this maximum is always at the same processor, right? Or sufficiently often at the same processor. Okay, the delete min operation is also similar to the first variant. Now I have in my SPMD pseudocode two queues, Q0 and Q1. Now I'm adaptively moving elements from Q1 to Q0. Namely, whenever the number of elements in our small queues, so the notation here is Q0 cup or Q1 cup means it's the union of all these local variables Q0 and Q1. So whenever the total number of elements in the Q0s that are smaller than the smallest element in the Q1s, whenever this number is less than p, I know I don't have the p globally smallest elements in my Q0s, and so everywhere I fetch one more element. So maybe that's another nice exercise for you. How can one implement this line in time order T collective? Okay, then we will do the selection as before, which I still haven't explained, right? Then as before, I use prefix sum to assign elements to processors. Now I don't have to check whether these are actually the p globally smallest elements because I ensured that already here. Okay, now for the analysis, the cost for the selection, the enumeration, and the delivery is the same as before. For the cost of removing locally, I said we can do each iteration in time order T collective, and the delete min operation in time order log n over p. But now the interesting part is how many iterations does this while loop do? And one can actually see that this is on average a constant number of iterations. I'm not going to give a formal proof here, but the intuition is basically that on average we remove a single element. On average we remove one element per local queue, right? And if on average we would remove more than we would do more than one iteration, then this Q0 would grow out of bounds. But that cannot be, because as soon as it contains a logarithmic number of elements, we know from this balls into bins things that it has to contain the p globally smallest elements. Thus, the only remaining possibility is that on the average, it's a constant number of iterations. So what we get overall is that we have a bulk insert operation in time order T collective plus the time for a constant number of local operations, and the same for the delete min star, which is asymptotically speaking the best we can hope for. I mean, these constant factors are not really small, but it's also not completely out of the question to implement and use that. So what's missing is the algorithm for selection, and I'm going to exploit here that the elements are randomly allocated to the processors. But I will do a substitution of my notation. So now n is the number of elements from which I want to select, because I don't want to have a complicated p log p that looks like it's specifically adapted to the priority queue case. and I want to select the element with rank k, and moreover I want to identify all the elements with rank less than or equal k. So in other words, I want to find the k smallest among these n elements. So the algorithm I'm describing here is actually very close to a very old sequential selection algorithm due to Bloom et al. From 1972. And it's also kind of related to quick select, but it's more sophisticated, and it's also related to sample sort, which you have already seen, right? So we choose a sample S, and now in something like quick select, you would perhaps choose a pivot among the samples that somehow well approximates the rank, right? So an element of S that has global rank close to k will have the local rank k over n in the sample, right? But the problem is for quick select, it doesn't really help to have a good approximation of the right rank, because in the recursion there will always be one big subproblem, and that's the one you will have to recurse on. So what we do here is we pick 2 rather than 1 pivot. And what we do is we pick one of the pivots u as a sample that is deliberately chosen somewhat too large, so that with high probability the elements we actually care for are less than or equal z. And on the other hand, we pick a pivot L with a rank that's deliberately chosen to be too small, so that with high probability all the with high probability most of the elements we want to select are actually smaller than z. And then we have a remaining problem that is small. Before I go into the formulas, maybe let me show it to you in a picture. So suppose these are our n elements in sorted order. We don't have them in sorted order, doesn't matter, it's just a conceptual picture. And we are interested in these k red elements. Okay, so now this sample element with rank k over n times size of S in the sample has in expectation just the right rank in the global input, right? So the black lines are the sample elements. But what we now do, so in reality, I mean, we would somehow get it someplace here or here, right? But what we do is we choose an upper bound U for pivot and a pivot L. And now we are classifying the elements into 3 categories, namely the elements less than or L. These are certain to be among the elements I want to return. The elements larger than U, these will certainly not be part of what I want, and the ones in between. And the idea now is that I only have to recurse on the elements in between. And the number of this will shrink very quickly. And that's what saves me basically a logarithmic factor in the running time of this algorithm. So mathematically speaking, we partition Q into the elements Q less that are less than L, Q larger of the elements that are larger than U, and Q prime that is the rest, Q minus Q less minus Q larger. Now we can check actually quite efficiently what we are expecting is that the number of elements in Q less is less than K, and that the number of elements in Q less plus the number of elements in Q prime is larger than or equal to K. So that's the case that we are expecting, and that by choosing delta appropriately, we make sure that it happens with high probability. In that case, we can output Q less and recurse on Q prime, looking for the K minus size of the number of elements in Q less in Q prime. So all other cases are unlikely, and then I can afford some expensive special case treatment in case this fails. Also, all these tests can be done with reductions in logarithmic time. So now guess what the sample size will be. Square root p. That's a hopefully simple question for you. Why square root p? And how can we then sort it in time order t collective? So now it gets a little bit messy, and I will not present the details of the corresponding analysis. But what we can do is to choose delta as p to the 1 over 4 plus epsilon for some small constant epsilon. And one can show that this suffices to make the difficult cases here sufficiently unlikely. We are not redistributing any elements. And here we exploit that we have a random initial distribution of the elements. I mean, we have some surviving elements, but which ones survive was just based on their key value, right? But their key value is independent on how they were allocated. So the recursive subproblem is still randomly distributed. And we can exploit that to say that, well, then we don't need to do any rebalancing. I'm stressing that because there are actually lower bounds on parallel selection that show that for arbitrary input distributions, things are more complicated, because then you can also do this trick here, but the recursive subproblem might have a highly skewed distribution of the elements over the processors. And then in order to maintain scalability, you first have to redistribute the data, which then can become a bottleneck. Okay. And basically what happens here, in the recursion, each time the remaining problem size shrinks by a factor that's a power of the number of processors. And that means after a constant number of iterations, the remaining number of elements, I mean, in our application for priority queues, n was p log p, right? Then on a constant number of iterations, we will be down to square root p. In case that, I mean, now we are discussing the general case, right? As long as n is polynomial in p, the same will apply. And then maybe a question you can look at is, what if for really arbitrary n, then we might need more than a constant number of iterations of this algorithm? And think of why this would still not violate an overall bound of time order n over p plus t collective. And I'm only expecting a qualitative argument here. You don't have to do a formal calculation. So let's discuss a little bit how we can further refine that algorithm, not with respect to its asymptotic performance, but to make it more practical, to improve the constant factors. And one thing is that if we really do this while loop here, whenever this condition is true, this means that the elements in Q0 that are actually smaller than this minimum in Q1 can be selected for the final output already, which then reduces the input size for the selection problem and might accelerate the selection. Or we could go the other way around and do a more aggressive removal of local elements, as long as this remains logarithmic size. And then we have less iterations of this loop. And of course, what is best in practice would be subject to some tuning of an actual implementation. And actually, there's a much larger number of tuning measures that you could try. So we could try priority queues supporting a fast merge in order to do this flushing of Q0 back into Q1 more efficiently. After that, we could perhaps look for a bulk delete min operation, which, depending on the representation of the queue, could also be faster. In the selection algorithm, we could use larger samples, which would allow us a more precise narrowing down of the subproblems, so thus reducing the number of iterations required. Also, with respect to the API, to the interface, we could say maybe our bulk delete min operation should not return exactly P elements, but maybe a much larger batch of elements. And then we would amortize all this coordination cost over a much larger number of elements to be returned. And maybe an exercise you could think about is, what would be the effect of larger batch sizes on the branch and bound algorithm? Maybe it's also instructive to look into the extreme case that the application actually does a lot of work with a task, say in this priority based scheduling thing, or say we have a branch and bound algorithm that does very expensive computations in order to compute a bound. Maybe it solves an integer linear program, right? Then actually the trivial centralized priority queue is actually not that bad. And the overall cost of communication operations would then be relatively low, because there will only be a trickle of requests going to it, right? And then it looks like there should be a middle ground. Maybe sometimes it also makes sense if there's only a small subset of processors that work as a priority queue server for all the others. And then finally, I implemented part of this, and in order to reduce to get rid of the costs of the relatively expensive selection operation, I actually did a suboptimal selection operation that, however, requires only a simple reduction. So very low latency in the communication at the cost of relatively long messages. So it turned out that by exchanging messages of size or the square root p log p, one can identify the order p smallest elements. And that's still much better than a naive algorithm. And if you have large startup overheads, that actually turned out to be advantages. So now let's think about an asynchronous interface, right? So insertions are no problem in this setting. We just send data to random queues. We can also do that in a shared memory setting by locking a queue and inserting data there, something like that. We can also use the batch delete min to fill a buffer of small elements. And then we basically have an adapter to an asynchronous interface by saying, oh, we need a FIFO queue that is served asynchronously that accesses this buffer. Actually, it's something simpler than a full FIFO because we only remove from it in a sense. And periodically we have to refill that buffer. And we also have to think about how inserted elements and the buffer will be accommodated. So maybe periodically we would commit the inserted elements, insert them into the local queues, and then merge the smallest elements from the local queues of the buffer, something like that. There's a huge design space, and I think it's worth exploring that because, for example, if you want to use a parallel priority queue for branch and bound, you don't really want this global synchronization after each batch. It's much more elegant and more robust with respect to load balancing if each processor just gets some small element whenever it is free to do that. So let's now think about experiments on that. So I implemented that a long time ago, 1996, I think. And I think it's perhaps interesting to report that maybe it's a little bit more historical interest, although I think that the implementation techniques are still relevant. One should, of course, redo these things in order to see what works how well on current machines. But still, I think one can learn a few lessons. So in 1996, there was a steep decline in parallel processing, basically because the sequential processors were getting faster and faster. That meant that basically even those people who still had parallel computers, they used less and less processors and still had performance improvements. So I did my master thesis on a strange, massively parallel machine with 2 to the 14 processors. Then I did my PhD thesis on a actually also quite strange machine with 1024 processors, most of the experiments. And then that was kind of shortly after my thesis. And then the largest reasonably up-to-date machine left in Karlsruhe that could do parallel processing was an IBM cluster with, I think they had 64 processors. But as an ordinary user, you could only get 32. That was it. And then to talk about scalable algorithm was a really painful thing. So what I did is, yes, I implemented this naive centralized approach and the parallel one with a lot of tricks to make latency small, even on a small number of processors. And then what we saw was, okay, the naive approach, the time for a batch operation goes up linearly, as one would expect, right? And here's an interpolating straight line. And the parallel algorithm, the good news is it's about logarithmic, the latency of it. But the overheads are so big that for 32 processors, it's still slower. I mean, one can try to interpolate this and see, yes, eventually it will help. Then I implored the people at the computing center. After a maintenance period, they gave me the entire machine for a couple of minutes. That was all I needed. I couldn't repeat the centralized thing because they had to run the code. And yes, that actually went on. And one could say, yeah, probably if this extrapolation works, which is likely, it is somewhat faster. But that's really not what you want to publish such a result, right? So in some sense, I was far ahead of my time there. Although I had the socialization with 2 to the 14 processors where this would have clearly been relevant, but that machine was switched off and, as I said, quite strange. So what to do? I had a friend who worked on the largest parallel computer in Britain at that time, which had 256 processes. And he actually ran the code for me, and then it worked out quite fine. The centralized approach took 28 milliseconds for an iteration. The parallel one, less than 4 milliseconds. And the break even was already at 34 processors. So that machine, a Cray T3D, had apparently lower latency communication, so the overheads were not quite as bad. So that was a successful result, and I think it would be interesting to try that on modern, really big machines. And actually we have several projects somehow going in that direction. Things are getting more complicated now, but yes, it's still an interesting basis for parallel priority queue. And theoretically speaking, almost perfect, right? So let me give you a little bit wider view of what other approaches are there. Another interesting, very elegant approach from the early 90s, I think, is that you generalize a binary heap to take nodes with p elements in each node sorted. And the invariant you have then is that all elements in a node are larger than all the elements in its parent node. And then there are ways to implement binary heaps so that you, or to generalize them so that you replace a compare and swap operation by a merge and split operation of two nodes of size p. So that's quite elegant, but it's also expensive because you have to sort very small data sets very efficiently. I'm not sure that works very well in practice. There was also another paper that said, okay, we have logarithmic cost for deleting a single element, so maybe we can parallelize that. And yeah, maybe not that surprisingly, that's indeed possible. You can parallelize a single access, giving you constant time for delete min using a logarithmic number of processors. But that is also quite limited parallelism, and I kind of doubt that the overheads for that would help you, would be warranted, and that overall you may not get a speed up at all. Another refinement that we looked at more recently together with my PhD student Lorenz Hübschle-Schneider. So what we did in that paper is we addressed this problem that you are randomly moving all the data in order to do insertion. And our focus here was communication efficiency. We want to communicate as little as possible. To me, that means whenever possible, do your operations locally. And then what we did is still a similar approach. So each processor has a local priority queue, but we now implement it as a search tree. And you can augment search tree data structures so that you can store subtree sizes, and then you can do a number of operations, in particular a selection in logarithmic time. Okay. You insert your elements simply locally. That takes logarithmic time, right? The constant factor might be slightly larger than for priority queue, but it's okay. And then we gave a distributed algorithm to find the globally k smallest elements in time order log squared k, but without moving around any of the elements, basically. And basically what we do here is something very similar to the multi-sequence selection that we discussed for parallel merge sort. Only that we now don't have a sorted sequence, but a search tree, but that can be adapted quite easily. And what we also observed is that there's a variant of the algorithm where you find the theta k smallest elements in just logarithmic time. So you don't have a guarantee whether it will be k elements or maybe 2k or 3k, but it will be in that ballpark. And actually that makes sense for many applications. For example, for branch and bound, we could basically say, okay, we process batches of elements in parallel, but it's not a big problem if the size of these batches varies by a constant factor between iterations. And we save a lot in the latency. So I think that's basically the modern variant of a distributed memory priority queue, where we are quite flexible, have low communication overhead, process large batches, and then I think this will scale to large inputs for certain applications. So somehow the small print in this communication efficient priority queue is you don't move any of the elements. You identify your k smallest elements without moving any elements. But of course, that can mean that some processors will have a lot of those elements and some have only few. And that's basically an interesting open problem depending on the application to find out how imbalanced can that be and how do you rebalance if the imbalance gets too big. But my intuition would be that this adaptive rebalancing would be much more communication efficient than eagerly moving everything around in a randomized fashion. So in the paper we also give we outline how to do this redistribution, and if you do it in the right way, you might have a steady state in the application where there is actually little imbalance. So that's something that we want to find out in the future. Now let's move to shared memory priority queues, and now look at a genuinely asynchronous interface. So again, we have sequential priority queues, and we distribute data randomly to these queues. But now we use use a constant factor more queues than processors, say 2p local queues, Q1 through QP. Insertion inserts data into a random local queue. So what it does, it picks a number between 1 and the number of queues. Then it locks this queue and inserts using a sequential insertion algorithm into this queue. We can do this in a kind of weight-free manner by saying, okay, if the randomly chosen queue turns out to be locked by some other thread, we simply choose a random queue again. And since there's a constant factor more queues than processors, we will have a constant success probability in finding an unlocked queue. We lock it, insert the element, unlock it, done, right? For deletion, one could use the same approach, just picking a random queue and doing a delete min of that. But one can actually show that then there will be some kind of drift that makes the errors in this queue relatively large. So what we do is we pick a sample of 2 randomly chosen queues and remove one element from the queue that has the smaller elements. And that turns out to be a stable approach. More precisely, for just finding out what are the minimum elements in these 2 random queues, there's no locking needed. But then in order to execute a delete min, you have to lock that queue. So let's look at the performance of a number of shared memory relaxed priority queues. So with relaxed, I mean that a delete min may not give us the actual globally smallest element, right? And there are actually now several papers that look at this approach to say we allow some errors, but then we get a scalable performance. So that's done on a relatively large shared memory machine. Here on the x-axis is the number of threads, and on the y-axis is throughput in mega operations per second. So large is good. And looking from bottom to top, there are two algorithms which basically show no speed up at all, right? They are, in some sense, exact priority queues. So they give a concurrent data structure, and you always remove the globally smallest element. And that, of course, is a source of contention, and that's why it doesn't really scale. One could also argue that it is not even precise, because there may be other, suppose you do a delete min, right? And you have a lot of delay because of contention. And while you are waiting for getting that result, there will be other threads that insert elements that may be actually smaller than what you are currently retrieving from the data structure. And they may also be delayed. So overall, there's no way to really have a global picture of the system in a concurrent priority queue, right? So it's very natural to relax it. And it looks like there's no way around it. Then there's a highly cited approach that's called spray list that basically uses a log-free skip list data structure. And the spraying means that it deliberately removes not the globally smallest element, but in a randomized fashion, something that's only close to minimum. And that actually scales considerably better than the seemingly precise priority queues. Although one should say this measurement is from a code that doesn't do, that basically is a huge memory leak. So you can run it for a couple of million of operations, and then the memory overflows. And this code didn't implement the cleanup stuff, and it might be that adding the cleanup would add a huge overhead to the program. So it's not quite clear what would be a practical version of this spray list thing. In contrast to that, our multi-queue is something that can really be used and doesn't have memory leaks. And we are comparing 3 versions of this. So basically what I have explained to you before is this green line. And it achieves on a single socket, which I think has 14 cores on that machine, a throughput of something like 30-something million operations per second, which is like 4 times better than the centralized ones and twice as good as the spray list. Then going beyond a single socket has some performance problem, but after that it continues scaling up to something like, I don't know, 50, close to 60 million operations per second, which is now truly twice as fast as the spray list. We will later see that it actually gives you a better precision. So what we are seeing is that all these algorithms scale much better on a single socket than on a multi-socket machine. So this dotted blue line actually says, rather than going to the next socket, I'm now using hardware threads on the first socket. And it actually turns out that it profits from using hyperthreading, giving us close to 50 million elements per second of throughput on a single socket with 28 threads. And then beyond that, we don't even actually get a big improvement. Eventually, we are matching the performance of the thing that gives just uses all the threads. And then there's a variant where we have doubled the number of queues, which reduces contention, but will also reduce the quality a little bit. And that one scales even better, going up to 70 million operations per second. Now we also have to look at the quality of this, right? So what we did is we set up an experiment that works only on a single socket, I think, where we are able to find out the actual rank of an element deleted. And one would like to have that the rank is always 1, right? If you have a precise priority queue. And you make a statistics of how often what happens. And now we can see that the spray list actually has fairly big errors. So here small is good, right? Our multi-queue with c equals 2 is much better actually. The multi-queue with c equals 4, that's a little bit more complicated. Most of the time it is also considerably better than the spray list, but there's a tail of cases where the error is actually larger. So here it's difficult to compare the quality, but one could perhaps argue that the multi-queue is better or of comparable quality than the spray list, and then that it would be a fair comparison to compare these two things where we have a factor of much more than 2 in performance. There's also a simplified theoretical analysis here that matches the actually observed values fairly good initially, but not for the tails. And probably the tails are due to locking, where occasionally you find locked elements have to go somewhere else, and then you get worse results. Okay, that brings us to the end of the priority queue chapter. The next thing will be list ranking, which is kind of a preparation for parallel graph algorithms. Thank you very much.